there does not exist positive integers m and n such that this equation is true. So I am claiming that this statement that you see is a true statement. And I want to show that it's true by pretending that this can happen. Let's pretend that this can happen. And under that pretense, we're going to run into a contradiction, which would imply that this cannot happen. And so the statement is true. So let me say this. Let's say this. Let's say suppose that m squared minus n squared equals 1 for some m comma n in the positive integers. Yeah, so that's z plus, z is the integers, plus is the positive integers. M and n are elements in here. So just as an FYI, what can m and n possibly be? The positive integers, that's the set that begins at 1, 2, 3, 4, and so on forever and ever and ever. Those are the positive integers. Now, let's suppose that this is true. M squared minus n squared. So we have this here. M squared minus n squared equals 1. Well, that gives us the following factorization. This is the difference of squares. That'd be m plus n times m minus n equals 1. The only thing that we know about m and n is that they're positive integers. So maybe one of them is 1, maybe one of them is 2. Maybe one of them is like a billion, and maybe the other one is like 24. We don't know. We just know that there's some number in here. But we can say this. Can we agree that there are two cases in terms of what m and n, how they compare with each other? M and n are either the same number or they are not the same number. There's no third case. So here's case 1. Case 1, let's say that in case 1, it should be a 1 right there. Case 1, m equals n. Let that be case 1. Case 1 says that m and n are the exact same number. I don't know what they are, but they're the same number. Maybe they're both 15, maybe they're both 100, who knows? They're the same number. Watch what happens to this, which is the same as that, right? These are the same. Watch what happens to this if m and n are equal. So let's pretend that m and n are equal. So this would be like this. M plus n times m minus, but look, instead of writing n, I'm gonna write m because in this case, they're the same number. And then here, that's m minus m, which is 0. So we have m plus n times 0 equals 1. And we have 0 equals 1. And of course, this is not true. This is totally false. So we want this to be true, right? We're being sort of rebellious. We want this to be true, but unfortunately, case 1 was a fail. What's the only other option? The only other option, case 2, if you want to call it that, is that m is not equal to n. M and n are not the same number. They are different numbers. Just keep that in mind. Okay. So what does that give us? So let's write this down again. So we have m plus n times m minus n equals 1. So if m and n are not the same numbers, then you know that this is not 0. And that's definitely not 0 because m and n are both positive anyways. Positive plus positive is positive. And you also know that this is not 0 because they're not the same number. And they're both positive numbers. And really, what's the smallest they could be? The smallest that m and n could be is like 2 and 1, right? And if you subtract 2 and 1, it's 1, it's not 0. So the point is, this is not 0, this is not 0 under this case. But now why don't we do this? You know that m and n are integers. And if you add integers, you get back more integers. So why don't we say this? Let's let m plus n equal p and let m minus n equal q, where p and q are in the positive integers. M and n are positive integers, so if you add them to get some other random letter p, that's also a positive integer. If you subtract them, that's still some number q in positive integers. Because what's the smallest that m and n could be? 2 and 1. If you subtract them, it's 1. 1 is still positive. Here's what I'm trying to get at. Let's write this down again. But instead of m plus n, we're going to replace it with p. Instead of m minus n, let's replace it with q. And the reason that I replaced m plus n with p and m minus n with q is just so that I can look at this with ease. When I see this, it's not as clear as when I see this. When I see this, I clearly decide that p and q must be 1. P has to be 1. Q has to be 1 because they're integers, right? P and q are positive integers. And if integer times integer is 1, then this and this have to be 1. It's not like you can be like, okay, 5 times 1 over 5 equals 1, where p is 5 and q is like 1 over 5. Nuh-uh, that don't fly, because 1/5 is not an integer. And p and q are both integers. So it has to be a solid times a solid is 1. This means that p equals 1 and q equals 1. So I'll just say like this implies or something like that. Little paragraph. This implies that p equals 1 and q equals 1. So let's take 1 and plug it in for p there. Take 1 and plug it in for q right there. So let's write down these equations down here again. We know that m plus n, which equals p, it has to be 1. And we know that m minus n, which equals q, that also has to be 1. Now look at what happens here. Why don't we take these two statements, these two equations, and add them together? Let's see what happens. If you go m plus n equals 1 and m minus n equals 1, if you add these equations, notice that the n's eliminate. M plus m is 2m, 1 plus 1 is 2. This tells us that m equals 1, and that's fine. I have no problem with that. But if I take 1 and plug it in for m, let's say right here, let's take 1, which is m, and plug in 1 for m right there. What would that equation say if we bring it back down here? That would say that 1 plus n equals 1. If you subtract 1 from both sides, this tells us that n equals 0. But look, this cannot be true. N cannot be 0. Because what was the assumption from the very beginning? The assumption from the very beginning is that n is a positive number. So case 1, there was a contradiction. Case 2, we have the symbol for a contradiction. So because both cases, the only two cases, were both fails, we say that we have a contradiction at hand. And so our supposition that this could be true is, of course, false, which means that the original blue statement stands true.